Thank you for coming. Our today's topic is Illuminating Villedor, lighting in dying light to stay human. My name is Wojciech Zeler and I work as a senior technology programmer. And during my career I've been implementing various rendering APIs in our engine such as OpenGL, DirectX 12, Metal, NVN. And in the meantime, I'm working on our post-processing pipeline, lightning FXs, and other rendering-related topics. And I'm here with Paweł Stolecki. He is our technical artist, and he's specialized in post-process effects, shaders optimization, and lighting. We both work at Techland. It's a company with more than 30 years of experience. And right now we have more than 400 employees. Our studios are located in Wrocław and Warsaw. However, most of us still work from homes. The company is known for titles such as Call of Juarez series, Dead Island, and Dying Light. We are proud to say that we've managed to sell more than 20 million copies of the first Dying Light game since its release in 2015. And what's more, we can say that we've sold more than 5 million copies of Dying Light 2 in just its first month after release. In the beginning, I will show you the difference between direct and indirect lighting, and later we'll focus on indirect lighting calculation in our engine. And finally, Paweł will tell you the details of how our screen space ambient occlusion works. Now I will show you two examples of direct and indirect lighting to make sure that we are all on the same page. Direct light is a light that comes directly from its source. In our engine, it may be the sun, a lamp, particle, or emissive material. In this case, our only light source is the sun. In this talk, I would like to focus on filling these black gaps with indirect lighting. Indirect lighting is a direct lighting that was bounced off any surface. I've marked examples of first bounce with pink arrows, while green arrows represents the second bounce. A similar situation happens in all interiors in our game. In this example, number of direct light sources is equal to 0. And the only way the light can reach our room is for it to bounce off the building that's across of the road and then enter through that window. Now, I hope that the difference between direct and indirect light is clear. So let's stay in this room a little bit longer, because for indoors we are using end probes. An end probe is just a volume filled with cells. A higher number of cells means better quality of final indirect lighting. Our artists have manual control over the density and placement of end probes. But before we can go any further, here is a short explanation of what spherical harmonics are. Let's think about a simple cube map. You can see it on the slide. But actually, for lighting purposes, generation purposes, we are using much lower resolution. 42 by 42 pixel is just enough for us. And spherical harmonics are a mathematical being that allows us to extract lower frequencies from an input cube map and create a simplified representation of it. And that's exactly what we need when it comes to approximation of light bouncing and global illumination. And what's more, spherical harmonics are a great compression technique because the input cube is around 24 kilobytes, while the output is only 56 bytes. And the end probe generation algorithm is pretty simple. First, we have to enable only direct light sources and generate a cube map. Then we need to compress that cube map using spherical harmonics. And then we can use these spherical harmonics as a light source in the nth probe, because in second bounce we enable only indirect lighting sources. And of course we still have to generate new cube maps and set of spherical harmonics. And the same thing happens for the third bounce. And finally, we just have to add together all these spherical harmonics and save them to disk, because we can later use them in our game. But the problem was the size and scale of our city. In the first Dying Light, each nth probe had only one cell. But in Dying Light 2, we decided to introduce cells because we wanted to improve the quality of indirect lighting. And while in Dying Light 1 needed around 6 to 10 hours for generation of its all 5,000 nth probes, in Dying Light 2 we had around 500,000 to 600,000 cells. That's 100 times more calculations. And in total, it makes around 27 million cubes to generate and transform to spherical harmonics. And we estimated that we'll need around 1 month for each indirect lighting rebuild in Dying Light 2. And unfortunately, one month was a little bit too much for us. So the first question we asked ourselves was, do we really need to calculate all of them? And of course, not. Sometimes it was fine to calculate only a part of the city, because production was focusing on that part at this moment. And on daily basis, it was enough for us to do an incremental build after each map build. It was mentioned before that we have 27 million cube maps to calculate and to transform to spherical harmonics. In Dying Light 1, that transformation was done by the CPU. It meant lots of GPU and CPU synchronizations and was obviously pretty slow. So we moved that part to shaders, because GPU is obviously better for such kind of computations. And we were able to calculate 500 cube maps with just few compute shader dispatches. And then we've noticed that you are wasting most of our generation time on drawing the same geometry again and again, because we have 3 bounces of light in interiors and 15 unique time and weather sets. So each cube map has to be rendered 45 times, at least. So we decided to introduce gbuffer cache. So for the first bounce, we are caching gbuffer and we are saving it to the hard drive. And then we only upload that gbuffer to GPU memory and apply Lightning to it. Our next observation was that our builders are too powerful for our code. Total usage of CPU and GPU was very low, maybe 10 up to 15%. And the idea was pretty simple. Let's start multiple instances of our editor, so each of them can process another part of the map in parallel. Of course, we're wasting some memory because we're loading the same resources multiple times. Fortunately for us, memory was not a problem, but time. So finally, we had one builder loaded with work to do. So the next step was to add multiple builders support. We ended up with 10 builders and 80 workers working on the same map at the same time. And the whole process was configurable through Jenkins. And we managed to reach 12 up to 13 hours for a full indirect Lightning rebuild. And that's still a lot, but it was acceptable for us, because it was happening on Saturday usually. Lighting data for all cities' interiors was around 1 gigabyte. And of course, we weren't needed everything always, but still, that's a lot of data because we have to maintain it, stream, generate, load, and so on. And additionally, artists have lots of work to put nth probes in proper places. And nobody wanted additional tens of thousands of nth probes, to put additional tens of thousands of nth probes across the city on outdoors. So we had to use a different approach. The algorithm for our voxel-based indirect lighting contains three major steps. First, we have our HDR scene. Then we need to voxelize it and update all voxel cascades. In the next step, we need to update voxelized irradiance using that voxelized scene. And then, in the next frame, we can apply that voxelized irradiance to our HDR scene. So that's the whole our voxel algorithm. Let's talk about voxelization. In the first step, in each frame, for each cascade, we randomly select a fixed number of samples. The number of samples depends on the voxel size in the cascade. 8,000 samples for the first cascade, 2,000 samples for the second one, and 500 for the last one. The rule is simple. The bigger the voxels are, the fewer samples are needed. And for each sample, we read its HDR color and depth value. Then we put this information into a proper 3D texture with a voxelized scene. Here you can see a debug overview of a voxelized scene. In the next 3 slides, you will be able to see a difference in voxel size and range between all cascades. Please note that all voxel cascades have the same number of voxels. So here is the first cascade. Voxels are 1.2 meter big, and the range is around 76 meters. Second cascade, voxels are 4 times bigger, so it's around 5 meters, and the range is 300 meters. And the last cascade, the range is 1,200 meters. For further objects, we are using skybox-based fallback. Voxelization affects only voxels that can be seen by the camera, but sometimes we will need to know what's outside of our voxelized area, for example, behind the player just after starting the game. We already had pre-baked height maps, which are 2-dimensional satellite textures with height information. They were used for various effects, such as rain particles clipping in the interiors. And these height maps were enough to create an approximation of the voxelized scene. So time for the next step, irradiance update. Time for the next step, irradiance update. Irradiance, just like voxelized scene, keeps its data separately for each cascade. And we are unable to handle 400,000 voxels, to update 400,000 voxels in every frame. So we have 3 queues. Each of them had a different set of conditions and priority. And finally, we are gathering up to 2,000 voxels to update in every frame. And I will show you in the next slide what a queue update looks like in our game. Please note that the brightness of voxel represents age of voxel, so darkest ones are the latest ones. And colors also have meaning, because I've marked with red color a missing queue, with green the visible queue, and with blue random queue. Pink represents uncalculated data here. So first you were able to see a blink of red color because everything was missing, and then we are only updating visible voxels. It's happening pretty fast, as you can see. Let's move to the remarching. First, everything starts with direction selection. We use Euler sphere because that gives us a specific number of evenly distributed directions on the sphere. Later, we use fast voxel traversal algorithm, and for optimization purposes, we are remarching through a tightly packed 3D integer texture where each bit represents a single scene voxel. And each remarch ends with one of three possible results. A voxelized scene hit, which is our best case scenario because it will give us a nice looking color bleeding. A height map based fallback hit, it will give us an approximate brightness. And in case of miss, a skybox hit. In the last step of the irradiance update, we must pack all sets of directions and colors into ambient cubes. To avoid popping, we are smoothly fading the new values over the old one. As storage for irradiance, we are using 6 3D textures, one for each direction, and 7th texture for an average value, because we'll use it later for volumetric effects. That's an overview of the irradiance buffer. Please note the red color propagation in the bottom right corner of the slide, and that green color on walls in the center. And that blue color comes from Skybox, of course. Here you can see a short demo of our directional irradiance. In the beginning, gathering for the update is blocked, and irradiance voxels are filled with default data, but then they quickly are filled with proper lighting. And now with filled irradiance buffer, we can apply indirect lighting to our scene from the beginning. As I've said, we can also use this data to lead volumetric effects. Here we have an emissive material as a light source. As you can see, it works as expected. And voxels are pretty cheap compared to ray tracing, which is also implemented in our engine. However, both techniques are quite similar to each other. They create a form of representation of the scene and then perform remarching through it. Voxels remarches through the voxelized scene, and ray tracing uses ray generation shader and full geometry info. Voxels are also less memory consuming because their size is fixed. We are using just a bunch of 3D textures and some helper buffers. In case of ray tracing, we need to create a bottom level acceleration structure for each mesh, and then we need to create top level acceleration structure in each frame. That takes hundreds of megabytes and a few milliseconds. And voxels work on every modern platform, including old-gen consoles like Xbox One and PlayStation 4. For ray tracing, you will need dedicated hardware, and the computation time is pretty high, even on high-end PCs. That's all from me. Thank you for your attention. Paweł, it's your turn.
Such an enlightenment, isn't it? So from now on, we will be dimming the lights. Thanks, Wojciech, dear audience. Voxels and end probes have a limited resolution, and because of that, they are unable to reproduce the high-resolution fine lighting details that you are expecting for a AAA game. To address that issue, we combine our existing ambient lighting with a screen space ambient occlusion that fills in the missing details, making it not only accurate but detailed. But what actually is an ambient occlusion? It's an extent to which a point of It's an extent to which a point on the surface is obscured from the lights. On the contrary, it says how well exposed to the lights is the surface point. If an AO value is 1, it means the surface is perfectly exposed. On the other hand, if it's black, it's completely obscured. I come from an artistic background, so it's always easier for me to explain things based on visual examples. What you can now see is a scene without ambient occlusion applied. And then let's see now what it does to the scene when I turn it on. As you can see, it heavily grounds the objects in the scene. It's ground the object in the scene. And that's how AO looks in isolated mode. Observe how the interiors and underneath of the cars are now properly darkened. Notice that the ambient occlusion is also making a great job in emphasizing geometric and normal map details, such as wrinkles on the cloth, mounts on the ground, and plating on the cars. So this is how the SSAO looks like in motion in location called the Bazaar. It was crucial for us to avoid visible ghosting, and as you can see, even on complex objects such as the netting, it is not present. Please draw your attention to how the different objects influence one another. Notice that under each object there is a shadow which helps to ground it in the scene. I've picked this location due to its rich depth complexity, strong normal map details, and interesting geometrical shapes. All these aspects are reflected in the AO you can see now. Okay, so since we now know how the ambient occlusion affects the lighting, I will now proceed to explain it, what it took to implement it. The algorithm has 3 passes. The first pass, ray marching, is responsible for computing a single half-resolution ambient occlusion sample for a given pixel. At this stage, the AO is pretty noisy, as you can see. The role of the following pass, the upsample and accumulation buffer, makes sure the data from the previous frames is not wasted, but accumulated. The last pass, the blur, acts as a denoiser to make sure that there is no noise in final output on the screen. So let's dive into the implementation details of the first pass, ray marching. Its role is to compute a half-resolution ambient occlusion value of a pixel. It does it by ray marching a scene in n directions in search for potential light occluders. It's the heaviest from all 3 passes due to usage of nested for loop, which can quickly and easily explode the texture sample and shader instruction count. We do a few tricks to get the most out of a limited budget, which is especially easily exhaustible on old generation hardware, which still needed to be supported. So the first trick is a hierarchical hit intersection validation. Ray marching is all about performing intersection tests. The number of tests a pixel can perform will vary across the screen. In pessimistic cases, it can be tens of tests will be performed. Each will require a depth sample to be taken. Since the texture sample sampling cost is heavily linked with its resolution, the texture resolution, we want to make sure that the texture that we are sampling is the smallest possible. The idea behind the optimization method is that we want to cheaply reject invalid hits by using a smaller size depth texture and only use the higher resolution depth texture only when necessary, reducing the overall cost. The half resolution texture that you can see is only sampled when the quarter resolution depth returns a hit. Yep. That's the idea behind it. Okay, the next thing that we need to take into the consideration when performing a ray march is to use a proper ray step length. Throughout the screen, the workspace distances between the pixels will not be constant. As you can see, the distance between few pixels on the bottom of the provided screen is few centimeters, but the same distance in pixels on the horizon is actually a few meters. We cannot use a constant ray step length to validate the hits and traverse through the screen. When small step length is used, we will accurately hit pixels close to the surface, but we will completely miss the long-range occlusion on the horizon, which is desired. On the other hand, when a large ray step length is used, we will most likely capture the occlusion from far from the surface, although near-field occlusion will be completely lost. We want both near-field and horizon occlusion. The key to that is to make sure our next step in the ray marching loop will move at least one screen space step, one pixel size step. If the length is below, we need to rescale the step. The code snippet that does it is provided below. We also need to take into the consideration how we validate the hit. Precisely the intersection threshold. What we do in our solution is called adaptive intersection threshold, and what is it exactly is that we link an intersection threshold to the ray step length. The ray step cannot be constant too, because if it's too small, we will simply miss the desired occlusion, and if it's too large, we will return a false, fake occlusion, which is undesired. And the solution to that problem is to use a ray step length as a threshold. Okay, so each sample direction is a significant cost. We can't afford to sample many of them within a single frame. To make the most out of a limited sample direction, we've chosen to use cosinus distribution for the hemisphere directions. This means we derive the sampling density on the hemisphere from the direction's weight. By doing so, we make sure the sample the I/O densely where the occlusion will really make a difference. On the provided screen, you can observe that the image with cosinus distribution follows the ground truth reference better than the uniformly distributed counterpart. The cosinus distribution is the image above the top. Okay, so since we are now finished with the first ray marching pass, let's move on to the second, the temporal accumulation. At this stage, we successfully computed a single AO sample. Let's now proceed to learning the following process of temporal accumulation, which was the key for achieving high quality within a limited budget. Temporal accumulation is a technique that splits the computation cost across multiple frames. This allows us to heavily reduce the cost while preserving the quality. Let's see it in action. Or not. At first, we see how the effect looks without temporal accumulation. It's quite noisy, it's all animated and wiggly. Once the accumulation kicks in, which should be just around now, the details are recovered, the quality is as desired, and there is no longer noise being visible in the video. Okay, so one would ask why the unaccumulated I/O was so noisy at first place. Why the noise was animated? To answer these questions, let me explain how we managed to integrate the whole hemisphere over multiple frames. Based on the value we read from that noise, animated noise, we sample a different set of directions along we seek for potential light occluders. Since noise is animated, every frame we change the value, which allows us to sample the whole hemisphere across multiple frames, which results in high quality ambient occlusion. Also, the noise you use is heavily important because if you use a white noise, for example, the AO during the accumulation will have a higher local contrast, and if you use a blue noise, for example, the local contrast will be lower, which will make the whole accumulation to be less visible. Okay, so that worked well. The whole temporal accumulation is a game changer, actually. It allows us to achieve a quality that wasn't in our reach before, but there is a catch. Sometimes the accumulated samples are no longer valid to use since the surface that we are currently shading have just appeared on our screens. Let's see the visualization of this phenomenon. As you can see, if the player moves, which happens very commonly in our game, if I rotate the camera when there is a high geometrical density and complexity in the scene, there is quite a lot of this occlusion happening, and we need to account for that. This video visualizes the age buffer, which value is resetted to 0, that is marked by the red pixels, when this occlusion is detected. If it's not, the pixel gets older and older each frame that passes by, which practically speaking means that we are accumulating the frames. Okay, to sum up this occlusion and age buffer, detecting this occlusion allows us to verify whether currently shaded pixel can use previously accumulated samples. We detect the disocclusion by comparing the current depth and reprojected depth from the previous frame. If the difference between them is large, we call the disocclusion. If it's small, we can accumulate. All this process is actually to prevent introducing ghosting, heavily undesired ghosting, to the screen. So there is no tails behind characters or any other animated objects. We use the age buffer to track pixels' age. It allows us to treat pixels differently based on their age. Freshly disoccluded pixels are more reactive due to being undersampled, and later on they are blurred more heavily to reduce the noisy load. I will now sum up the second pass called temporal accumulation. Firstly, we need to upsample the AO from half resolution using bilateral weights. They are needed to eliminate the ghosting caused by linear filtering between the pixels. Then we check whether the disocclusion has happened. If it did, we reset the pixels to age to 0 and return the AO without any accumulation. If there was no disocclusion, we accumulate currently processed AO with accumulation buffer based on the blend factor derived from the pixel's age. If the age is high, like it's old, the blend factor can be lower, which allows to accumulate more and quite a significant amount of samples. And if the pixel is young, we need to drastically, fastly update the value of an AO in this pixel. So the final step in the algorithm is a blur pass. It acts as a denoiser for freshly disoccluded pixel, which for a couple of frames are too noisy to be presentable to the player. And let's see the differences visually. So this is the screen without any accumulation, without any blur. It looks pretty noisy. It's unacceptable to be presented to the player. This is how the effect looks after the blur. Of course, we lose the detail, but the noise is gone. And this is not a problem that we lose the detail, because this version of the AO is only visible to the player for a couple of frames. And we only need to make sure that the noise doesn't draw his attention to the place. And if it's blurred, it's like you don't draw your attention to the blurred pixels. So it helps heavily. And just for a reference, this is how the fully converged accumulated I/O looks from that view. So summarizing the blur pass, its main role is to denoise freshly disoccluded pixels. This way we spatially recover missing temporal information, and in simple words, if a pixel is not enough, we borrow the information from its neighbors to improve its quality, since we don't have the pixels from the previous frames. And as you can see, we've managed to keep the AO cost on all generation hardware in reasonable values, which was a core requirement. The algorithm also scales well on current generation hardware, where features like native 4K resolution rendering is expected. So the AO scales well. The small side story to the whole development process is that at the time when we initially started the production on the new SSAO algorithm, we had already ray traced AO solution implemented. We're very satisfied with the results it was producing, and we consider it as a quality benchmark. It was very influential to the whole development process. It helped to make the right decision, and we think we managed to get very close to the ray trace quality while staying very low cost. The comparison is as you see. We are missing the occlusion from the objects that are outside of the screen, but when the potential occluder is inside the screen, we precisely detect this, and the quality is quite close. The results are quite close. So now I will summarize the whole presentation. So this is how the scene looks without any indirect lighting. As you can see, in the areas in shadow are completely black. Now we recover the missing indirect lighting by introducing voxels. And we detail it by using ambient occlusion. And these were the resources we use to produce voxels, nth-probes, and screen space ambient occlusion. I heavily recommend reading on practical real-time strategies for accurate indirect occlusion by Ryoku. That was, I think, the most influential for me for production of the screen space ambient occlusion technique. Okay, and thank you for your attention, and we are now open to the questions with the Wojciech.
Thanks again for your talk. Can you a little bit elaborate, because at the beginning of the presentation you've shown nth-probe-based technique, and it looked like it's a bake technique, and then you showed a voxel technique, which was more of a real-time technique. So do you use both? And if yes, how do they coexist in your engine?
Yes, we are using both of them, and we have a special kind of nth probes which we call blending nth probes, and we can smoothly blend between those two worlds, let's say.
And what's the reason? Is one is more accurate than another?
Env probes are have much bigger precision because we are pre-baking them, and it means that we know everything during calculation, while voxels knows only the same thing that you can see. That's all.
Okay, one more question before I yield to the next one. How do you recalculate lighting if you have like dynamic time of day, and whether the ENV probes are basically like capturing only the global light, or do they also capture the local light? So in that situation, how do you change? How you handle dynamic day and night cycle, and or switching on off the local lights if you use them, and that would be.
I've said that we have 15 unique time and weather sets, and we are blending between them. That's answer for the first part of the question. And for blending between these sets, in case of ENV probes, we just load 2 sets of spherical harmonics and we blend between them. In terms of voxels, we are smoothly, that's a nasty thing. We are smoothly disabling them for a while, and then we're re-enabling them with new lighting because we have to clear them. We don't want to let players see white voxels, for example, during night because they were not updated.
Thanks a lot again.
Hi, thanks for the presentation. I was wondering, when you were talking about baking the light for certain parts of the game because production focuses on these parts, I was wondering, how do you establish which lights can have to be rebaked? Do you do that with every commit? Do you establish which environments were changed and decide recompilation based off that, or do you do it manually where you select presets of where you have to recompile the lights?
So for partial builds, which were mentioned before, our scene is a tree, and we are able to select one node of that tree to rebuild, so everything that's below it will be rebuilt. And incremental builds are tricky because every ENV probe has its unique ID, and in case of missing data, we just need to update these missing ones. Plus, of course, it's neighbors because light can travel between 2 ENV probes, and we don't want to skip that part. Okay, I think that's all. So thank you once again.